All right, here we are with a differential equation from the BC test in 2008. And just a little bit of background. This is technically a logistic equation, which I know scares some people, but it's just the type of equation it is. And if you were to solve this, which actually doesn't ask you to do, surprisingly, usually it does. But if you were asked to solve it, you would separate the variables where you'd have kind of a 1 over y and a 1 over 6 minus y dy, and you'd have like a 1 over 8 dx. And usually logistics, this is where the partial fractions come in. And so I totally think they could put that on there and actually ask you to solve it. But one of the reasons I like this question is it kind of takes a scenario with a differential equation and then ties in some other kind of big concepts. And I think that's what they're going to do on the national exam, is try to cram in as many concepts into one scenario as possible. So if you want an extra exercise, this is where you have to try to separate them, find the a and the b, a over y plus b over 6 minus y, kind of go from there. Go for it. But let's actually do this one that sets up here. So part A, it says a slope field is actually given. Sketch possible solution curves through the points 3, 2, and 0, 8. And those points are labeled on the actual graph. And that's where you kind of just look for the flow of the graph. And, to me, you want a curve it looks like it's kind of coming down here and then it levels off towards this asymptote. You have all these different curves. And so one curve would kind of be like this. That's the one that's passing through 0, 8. And you'll probably go up like this. And then the other one, it looks like it's leveling off down here, kind of going up and kind of wavy looking, so maybe something like this. They could ask you that on your exam. I mean, it goes quick. Remember, time is the big challenge. So, all right, a few of you have asked me about Euler's method. Usually it comes up with differential equations. And it's an approximation for a differential equation that either you can't solve or that's a pain in the butt to solve. If you were asked to solve this, it would take a few minutes at least. But Euler's method works something like this. Usually it gives you a point to start with. So I'm going to set up my t and my y, and it's telling us to start at 0, 8. And then it says 2 steps of equal size. That's a hint on what we're going to use for, in this case, dt. Sometimes it's dx. So if we want to use 2 steps, but we want to approximate 1, that means we have to end at 1, which means our dt in this example would be 0.5, similar to Riemann sums. And then the idea here, the big picture, is we're going to think of finding our new dy, which is going to be y over 8 times 6 minus y. And then move that dt over here. And in this case, dt is going to be 0.5. The dy that we find means the change in y, and we're going to add that to 8 to get our new y, and then repeat that process twice. So, for example, our first dy, we'll call it dy sub 1, is going to be my y value that we're starting with, divided by 8, then 6 minus my y value, and then times dt. So I've got 1 times negative 2 times a half. So half of negative 2 is negative 1. That means my new y, and my new point, I'm going to subtract 1 from 8. So it's not too bad, it just looks like a big mess. So my next dy is essentially the same process, except my new y is 7. I'm going to substitute that into my differential equation. My dt is still 0.5. So it looks like I've got 7/8 times negative 1/2. You can pause it and check the math if you need to, but I think it's right. So I got negative 7/16. And so my approximation would be 7. And then my new dy would be 7 minus 7/16. Now, if all was right in the world, we would just know the answer, come up with the common denominator. But this is the national exam, and we got to move quickly. So I'm just going to leave it as 7 minus 7/16, and they would give you full credit for that. But you could simplify it, so to speak, if you wanted to. Mixed number, improper fraction, whatever. All right, let's move on. Let me clear up some space here. Soak it all in. It's beautiful. All right, letter C. Says write a second degree Taylor polynomial for f about t equals 0 and then use it to approximate f of 1. All right, so the definition for a Taylor polynomial looks something like this. So I'm going to write it out. We're going to be working with this a lot in these last few weeks. So the idea is you can approximate a function using a polynomial. But this says at about t equals 0. And so this is the definition, but we're not going to be using x's. We're going to be using t's. So that's just the notation that scares some people. And so what this really becomes is it becomes the point is at 0. So it really becomes, the approximation is f of 0 plus f prime of 0 t minus 0 plus f double prime of 0 t minus 0 over 2 factorial. And it says second degree, and so a Taylor polynomial can actually go as far as you want it, but I stop at degree 2 because it tells me to. If it was a third degree Taylor polynomial, then we'd have an additional term. And the next term, as you might remember, would be a cubic term. Okay, we have some of this stuff. F of 0 is 8, so that's this. And then this t minus 0 just becomes a t, but we need f prime of 0. And remember, f prime is the same as dy dt. So I'll do a little note down here. If dy dt, that means the derivative of y with respect to t. But the derivative of y would be f prime of t. So dy dt is going to help us find this coefficient right here. It's y over 8 times 6 minus y. Now, one of the hardest things that I thought about this problem that really challenges me, challenges you, is that this differential equation is in terms of y, but the value we were given was a t value, t equals 0. But when t equals 0, whether you're looking at 0, 8 on the graph, or you just see it come together, when t is 0, the corresponding y is 8. And so to find that slope, dy dt, I would plug in the 8 here. And it looks like I'm going to get a negative 2. That is f prime of 0, which is the thing required for this Taylor polynomial. So that's going to be a negative 2 here. The third term, you might see I have a t squared there. I have a 2 factorial down here. That's part of the definition. But I still need to find this second derivative. And the logic's going to be the same down here, except I need to find the derivative of the derivative. I need to find d dt of dy dt. Again, the notation's kind of gnarly. Let me clean up some space here real quick. And so in English, I need to find the derivative of the derivative. So I need to find d dt. That's the derivative with respect to t of dy dt. That will give me this fun one that we like, looks like this. But what I really need to do is take the derivative with respect to t of this differential equation that was given. And that's going to require the product rule. So see if you can follow along with this. U prime, there we go, U prime v plus u v prime. Again, the negative 1 is the derivative of negative y. So that's my second derivative, and that's going to be used to calculate this box up here. Hope you can't hear my stomach, it's like growling. So if I want the second derivative at t equals 0, again, the corresponding y value for t equals 0, I had it up here earlier, I erased it, is y equals 8. I'm going to end up having a 1/8 6 minus 8. I'm plugging in 8, not 0, plus 8 over 8 times negative 1. So I think the second derivative at 0 is going to be negative 2/8 minus 1, which is negative 1 and 1 minus 5/4. And so that second degree Taylor polynomial is going to look something like this. And again, we could simplify that 5/4 and 2 factorial. But for now, just so you can kind of see the structure a little bit, we'll leave it like that. Sometimes these Taylor polynomials, they use like a p to represent a polynomial or something. So I'll leave it like that, and I'm sure we'll talk about it more. The last question, just to bring closure to it, says, what's the range of f for t equals 0? So f is the function that passes through 0, 8. And so it's kind of deceiving here, and maybe they just, want to give you a couple extra points at the end, and I don't know if they're going to ask this, kind of one of those random questions, but it says when t is greater than 0, so I'm only looking at things to the right of the y-axis, but it's really asking me for the range of this curve. And there is an asymptote there, looks like it's 6. So I would say the range is going to be greater than 6, but less than or equal to 8. Kind of wrote it backwards there. So I would say that the range is, oops, I got that inequality wrong. The range is going to look something like this. So, all right, there's a lot going on here. I think it mixes ideas well, but it definitely is tricky. So check it out, look at it. Hopefully it helped, and thanks for watching.